quick look at what we did in the exponential functions and finance unit. It's broken into two parts. Part one was strictly exponential functions. And we right away started looking at growth and decay situations where we were writing down our own equations based on the scenario. Okay, so the exponent t is a variable, and over here the allowance depends on t. Here the number of sharks depended on time, and here a population depended on time. And if we notice in the denominator of the exponent, that's how often things double. Here it happens every 3 years where the shark population seems to decay. We also talked about half-life, and typically those are questions that come up on evaluations as well. And this is sort of the generalized formula of everything that's happening. All right, we start with an initial amount. It has some kind of growth or decay over time. N tracks how often the growth or decay occurs, and you end up with a final amount y. In the second lesson, we took a look at graphing exponential functions, and we were asked to find their domain range, x, y intercepts, any asymptotes, and whether they increase or decrease. So we used Desmos for this. You might want to have another look at that because there may be a question like that coming up on your evaluation. For our third lesson, we looked at how exponential functions can be transformed and then graphed. And this was done in a video lesson, such as like y equals negative base 2 exponent 2x minus 6 plus 5. We said it was no different than having some kind of parent function, where the parent function here would be y equals base 2 exponent x. And you go through its reflection stretches and translations, and those result in the development of an RST chart. And you use key points that get transformed based on the outcome of your RST chart, so you can graph exponential functions. Any exponential function can be graphed this way. As part of the practice to try and graph any exponential function, here's a typical question. So sketch the graph of y equals minus a half base 2 exponent x minus 4. And here they tell you who the parent function would be. Y equals 2 to the x is like a parent function. So you'd want to use an RST chart, go through the same steps we did last unit, and or the unit before, so you could graph this. And then usually we ask you to state the domain and range, any intervals of decrease or increase, decrease. The second part to this unit was all on finance, and we developed several formulas depending on the situation, from simple interest to compound interest into annuities. All right, let's take a look at that. Each financial situation we looked at often dealt with several variables, and we sort of tracked them all on our formula sheet, and here they are. So these are definitely things you want to become comfortable with. We did end up calling the idea of a quarterly, monthly, bi-monthly type of investment. We ended up calling those numbers the magic numbers, since they come up in every financial question that involves compound interest. Our first lesson was simple interest, where the interest I is equal to PRT, the principal with rate and time. And we quickly learned that all the time our time needs to be in years. So just make sure if you're given months, it's got to be in years. If you're given days, it's got to be in years. Have a look back in the lesson where we developed like a linear model. We didn't use A. We said it was F for the future amount. So F equals PRT plus P. And we reminded you that that's sort of like a linear model from grade 9, like y equals mx plus p. And we had questions like this in the lesson, and even the next day we came into class and did a practice quiz on this topic, where your money doubles and you use your linear model to solve for how long that takes. So you can go back over that. Then we reached the point where we started talking about how interest is calculated in a way such that it's compounded. In the simple interest scenario, you put $1,000 in the bank, and every year you'll just get $50 in interest. Not likely. More likely is the fact that you deposit $1,000, get 5% interest. In the first year you get $50, but then you reinvest that money and end up earning higher interest. And then you reinvest it again and you end up earning higher interest. And the interest here goes up exponentially. And since this is very typical for financial investments, we have to track these compounding periods, how often the interest is calculated, using a magic number. So we sort of developed these types and said that these were the equivalent magic numbers for each. So if we compound interest, we can actually calculate the future value of our investment with one formula. And it's right here. The future value equals the present value times 1 plus I exponent n. So exponent n makes this an exponential function. All these finance calculations, except for simple interest, are exponential functions. What happens is you're given a scenario where the bank gives you a simple interest rate or an annual interest rate, and you develop I, the compound interest rate, over several compounding periods. And you're able to calculate the future amount of your investment. So one investment gives one future amount. For instance, we had bought a MacBook, and it was a $3,000 MacBook. If we use this investment as a 12% annual interest, it ended up costing us $5,372.54. We had an example too where we had Angela, and she applied for an $8,000 loan at Scotiabank and repaid it over 4 years. And we had to find out what the interest rate was for this to take place, and went through the same formula here. Sometimes you'll see FV for future value and PV for present value. It's the same thing. This should just read F equals P, 1 plus I to the n. Once you solve this, you needed the fourth root. You could really come up with any root depending on the different questions, but you have to be ready to take any root and be comfortable doing that with your calculator. Okay? Just make sure if you're doing a question like this, yes, we did find the compound interest rate, 9.5%, but it's actually the little r rate we need to find. And in this case, it was the same, okay, because the magic number was annual compounding of 1, but it can be different, and you would use this little formula to adjust for that. Just want to quickly point out, this exponential function that calculates the future value of our investment is a growth type. And you know that because n, the variable that we mostly track, the exponent, is positive. This takes us right into our next lesson, where now we are aware of what the future amount we need is, and we want to know what we have presently. And here the exponent's negative. That's because this is an example of exponential decay. It's the opposite of earlier where it was exponential growth. The negative exponent makes this exponential decay. So we had Kyle, and he wanted to save for $1,000. In 4 years from now, he wants $1,000. So that's a future amount he needs. And with this new formula and the investment as described here, we were able to find what he presently needs in his account. So 4 years from now, he has the $1,000 to buy his computer. So it turns out he only needed $774.25. So we can see that the present value is less than the future value, which is the case when you're dealing with money. Money will grow as time goes on due to interest accumulating and compounding on the investments. Next up, we looked at annuities. See, annuities are more typical. Usually you don't go deposit one amount of money and leave it there for like 10 years and then come back to it. Usually you deposit regular amounts of money. So R was the regular deposits. And you can calculate, again, the future value with one formula. I'll remind you, FV is no different than F. Sometimes it's written as FV. So the future amount of our regular deposits with an investment as described by I and N can be calculated. We also showed this for, say, in example 1 with what's known as a timeline. And the timeline shows you how all the deposits go through and get calculated with their interest. So you set up your long timeline, and you have all 36-year periods, but you use dot, 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 because it just means the pattern continues. And then you have all your deposits, $100, $100. Here I should have had a dot, dot, dot. and then all the $100 deposits. And then we notice the last deposit does not have any interest put on it because the investment ends. As soon as you make that deposit, the investment ends. It has no time to get interest. This deposit happened just previously. It had one chance to have interest put on it. And this one had two chances. If we follow it, it had interest put right away, right here, and then it came out. And this pattern just continues. There's the dot, dot, dot. This happens all the way to exponent 35. And if you think about that, that's 36 occurrences. This first one, this is the second one, that's the third one, all the way to 36 total. This one's exponent is not shown. It would be like 0. So with that regular depositing of $100 every month, so 36 of those deposits, because it's over 3 years, we're actually able to find the future value. And it's just that formula for this particular type of investment. You have to be very careful that you're doing the BEDMAS rule. You come in the big square brackets, you add up 1 plus I, and then exponent 36 goes in your calculator first. So 1.005 exponent 36, hit equal if you must, subtract 1, multiply it by 100, and divide by 0.005. Make sure, too, your final answers involve 2 spots because it's down to the cent. $3,933.61, okay? I also ask, how much interest will the annuity have earned? Well, think about that. This is 3 years, 36 times we invest $100. So 36 investments of $100 is like saying there's 36 deposits of $100, and that's $3,600. Therefore, the interest is just what the future amount is. It has to be bigger. Subtract all the original deposits. If you could imagine, they were all done at once. So then you end up finding out how much interest was accumulated in this particular investment. We also looked at an annuity where Peach knew she needed $4,000 for university tuition when she graduates in 2 years. So she's going to make all these deposits right now so she can achieve this goal. Okay, and we showed this with a timeline. You can really see it if you draw a timeline. She's making some deposit, R, each time. I should have 3 dots here. R, 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 R. Okay, that means we can still find R. Even though it's not given, we were still given she wants a future amount of $4,000. So yes, you can draw the timeline without knowing the regular deposit amount. And then yes, with the info giving in the question, F being a future amount of $4,000, 52 deposits, we can still find R. You just have to go through and solve this like the example we did in class. Okay? So here the regular amount she achieves $4,000 in her timeline is a regular deposit amount of $72.13. Okay? Pointing out too, if you do end up calculating this in parts, get as many decimal spots as you can with these bigger numbers. It'll just make things more precise. Something else to point out, if you look at this exponential function where the future value is equal to some exponential relationship, this exponential function is a growth type. N would be the independent variable, FV would be the dependent variable, and because n is positive, this is exponential growth. As you deposit R values regularly, your future value keeps growing, which takes us into the next lesson. Here, which is the next lesson, and then the last lesson of the unit 2, we've got the present value who seems to vary with negative n. So negative n is an exponent who's our independent variable, and he generates a present value. So this is an exponential function of type decay. The exponent being negative tells you it's decay. So if we make R withdrawals, you're taking money away, you're decaying the value of money, you end up being able to calculate what the present value is over this investment. Okay, so it's like last lesson we looked at annuities where we had no present value and we grew it by making regular deposits. This lesson is one where we actually kind of knew what we had and we withdrew it regularly to end up with nothing left in our bank account, a future value of 0. For the present value of an annuity, we looked at a situation where Brad and Angelina, or Brangelina, were retiring. And they were withdrawing $100,000 a month for 20 years. And they decided to use a 9% investment compounded monthly. Notice if you're withdrawing or even depositing money monthly, you have to also compound monthly. The compounding frequency has to equal the withdrawal or deposit frequency. So Brangelina here, taking out $100,000 every month can be drawn with a timeline. So over 20 years at 12 times a year, that would be 240 different withdrawals, each time taking out $1,000. And we said we had to sort of take the first withdrawal back to now, back to the present. So we send it back and we sort of undo the interest with this little formula, R over 1 plus I to the n. So it comes back. That is not the 9% interest rate. Remember, that is I. I is 9% in this scenario. Divide by 12 because of the compounding done monthly. And you generate your timeline. It's got the same pattern as last time. The first withdrawal loses 1 chance. This one has an exponent 2 for 2 chances of interest. 3, ... all the way to 240. So then the big question is, if Brangelina is withdrawing $100,000 a month for 20 years, how much are they withdrawing? Well, you could say to yourself, well, $100,000 a month, 12 months a year, 20 years, that should be $24 million withdrawn. But it's not. They have money in their bank account right now, some amount, and it's going to generate interest for 20 years. They will take out $100,000 each month, but they don't need $24 million in their account right now. If we use this formula, the present value of annuity, and we have R as $100,000 a month with the investment properties, so we've calculated I and we've got our N, we can take this and calculate that we actually only need $11,114,666.67 in our bank account. Whoa! So they're going to actually withdraw $24 million worth of money, but all they need today is less than half of that. So that sums up all the topics, the 2 different parts to our unit. Here's a look again at the finance formulas. These are ones that you'd want to commit to memory. Now, for the long series that the annuities generate, they're easier to see in a timeline. The best thing that prepares you for the upcoming evaluation, our test, would be, you've seen everything in the lessons, get all the concepts, the examples make sense. You've practiced each day's assigned homework and done your best to find out what went wrong, if you're checking your answers, getting help. Also, on our Google Classroom, you can find all sorts of review. Now, this is more than you could ever need. Okay, the review's been broken down, so it's more than anybody needs. It's been broken down. You've got growth and decay, exponential function properties, graphing exponential functions, simple interest, compound interest, and then annuities. Okay, you can pick and choose where you need the work. So you'll even see like exponential functions review with full solutions. There's finance review with solutions. There's even a practice test, which is an old test. There's solutions, and even the old worksheet on growth and decay with half-life. So you have to sort of aim maybe to do 50% of this, but targeting areas where you need the work. You know yourself, everybody's different with their needs for math, so just target it to suit yourself. Best of luck. One last thing though, if you leave a comment on this video lesson right on YouTube, log in with your Halton account, with your Halton password, use your Halton email, and leave a comment on this video lesson, and you will earn 1 free mark to start your test off coming up. So again, just leave any comment, make sure it's appropriate, and that's 1 free mark starting you off on your test. Best of luck. Thanks.